In this video, we're going to talk about a method for solving equations based on derivatives. It's a numerical method, so it only gives an approximation usually, but it's very useful. Alright, so the question might be something like, how do we solve an equation such as 2x plus 1 equals sine x? This might be very difficult to come up with an exact answer, but we can use Newton's method to come up with an approximation that's as close as we want. Alright, so what do? We first rewrite the equation in the form f of x equals 0. So in other words, in this case, we would write, for instance, 2x plus 1 minus sine x equals 0. And the 2x plus 1 minus sine x is the f of x. Now, what you've got is an equation of the form f of x equals 0. So solving an equation of the form f of x equals 0 really means finding x-intercepts for this function. Right? So if f of x intersects the x-axis, then we are finding that intersection. So Newton's method, which is named for Sir Isaac Newton, starts with an approximation, or what you might call an initial guess, of an actual solution, and we call this initial guess x1. Now here's what happens. So imagine that this is the f of x, and we're trying to find this x-intercept. So we make an initial guess, x1, that is here on the x-axis. So what Newton's method does is this. It goes up to the corresponding point. It starts at x1 and goes to the corresponding point on the graph of f. So this point has x-coordinate x1 and y-coordinate f of x1. And it draws a tangent line, a line tangent to this graph at that point, and with any luck, this tangent line will cross the x-axis, and where it crosses the x-axis, that's x2. That's the next approximation, and in this case, it is closer to the actual value than the initial guess of x1. Now, to repeat this, we would again go up to the point on the graph with x2 as its x-coordinate, draw the tangent line. I'm at a bit of an odd angle, so it's hard for me to draw a straight line. And then where that tangent line crosses the x-axis, that's x3, and so you see we're getting quite a bit closer, and we can keep that up until we're as close as we want. Now typically what we do is we look for two consecutive approximations, an xn and xn plus 1, so that are fairly close together, say within 0.001 or something like that. And at that stage, the last approximation we get is our final approximation. Alright, so this is a pretty good method. However, there are some pitfalls. An obvious pitfall is picking x1 at a point where the graph of the function f of x has a horizontal tangent line or is not differentiable. What's the problem there? Well, if you pick a point where where f of x has a horizontal tangent line, then that horizontal tangent line will never cross the x-axis. It'll run parallel to the x-axis, so you won't get an x2. Or if you pick a point where the function isn't differentiable, there won't be a tangent line at all. Some more interesting things can happen, such as this. you might pick an x1 and then the tangent line, you might pick an x1, then the tangent line at x1 sends you to a point x2. So for instance, in this case, we're looking for one of these two x-intercepts. So we pick a point close to one of them. The tangent line sends us over to x2, which isn't really any closer than x1. But then when we try for another approximation, the tangent line sends us back to x1. And so we would keep bouncing back and forth between these 2 points without ever reaching one of those intercepts or even getting close. So that's kind of an odd little thing that can happen. Another thing that can happen can occur where you have a situation with a horizontal asymptote. It might happen, such as in this case, that if you pick for your initial guess x1, that the tangent line might send you over to where the graph is starting to follow the horizontal asymptote. Then, if you come down here to the point on the graph, the tangent line is going to be in this direction, and where it crosses the x-axis is even farther down that way. And the more iterations of this method that you use, the farther down the positive x-axis you go. You never do get close to the solution. But despite all these problems, this is a good method, because these things don't happen all that often. This one in particular is very strange, and everything would have to line up exactly against you for that to happen. Alright, so Newton's method, how does it work? What are these steps involved? Well, you first rewrite the equation so that you get 0 on one side, and then this is your f of c, or f of x. You make an initial estimate, x1, that we think is close to the solution c. Then you use this formula to get the further approximations. So this is the ith approximation, and then to find the next one, x sub I plus 1, you take the last one that you found and you subtract off f of xi divided by f prime of xi. And then when you reach the point that the difference between two consecutive approximations is within the desired accuracy level, you stop, and the last approximation you find serves as the final approximation. And a bit of terminology, each application of this process is called an iteration. So let's use Newton's method to approximate the square root of 5. Now, I didn't give you a function here, so you may be wondering, how do I do this? There's no equation. Well, we make our own equation. We start out by letting x be the square root of 5. Now, is there anything we can do to this equation to get an equivalent equation, but without irrational numbers? Can we get rid of that square root? We can if we square each side. And now here's the equation that we want to solve, x squared equals 5. So, we need to rewrite that as x squared minus 5 equals 0. This part here is the f of x. We need to find f prime of x. That's going to be 2x. And we need to make an initial guess. Well, the square root of 5 is going to be bigger than 2 because 2 squared is 4, but it's going to be smaller than 3 because 3 squared is 9. So how about we use as our initial guess x1 equals 2. Alright, so how do we find x2? Well, x2 is going to be x1 minus f of x1 over f prime of x1. That's just using this formula. So again, the I is the subscript of the most recent approximation, and then this is the subscript of the next approximation. It's going to be one more. So x of 2 is x1 minus f of x1 divided by f prime of x1. So this is going to be 2 minus f of 2, which is going to be negative 1, right? 2 squared minus 5 is 4 minus 5, or negative 1. And then f prime of 2 is 4, and that's going to be 2 plus 1/4, 2.25, but I think I'm going to write that as 9/4 because it'll be easier for the next iteration. So 2.25 is not a bad approximation. It's closer than 2. Well, let's go ahead and find x sub 3. So how would we find x sub 3? Well, x sub 3 is x sub 2 minus f of x sub 2 over f prime of x sub 2. So this is going to be 9/4 minus f of 9/4. F of 9/4 is going to be 9/4 squared. That's 81/16 minus 5 would be 80/16, so that would be 1/16 divided by f prime of 9/4. Again, that's the x2. We're substituting this in to the function and to f of x and f prime of x. So f prime of 9/4 would be 9/2. So that's going to be 9/4 minus 1/16 times 2/9. So we've got 9/4 minus 1 over 72. Now if we find a common denominator, let's see, the least common denominator would be 72. We need to multiply this by 18 and that by 18. 9 times 18 would be 162. Subtract the 1, that would be 161 over 72. So I got 2.236 with a repeating 1. And then I also used a calculator to give me an approximation for the square root of 5, and I got about 2.23607. So we are correct up to 3 places after the decimal point. So with just 2 iterations, we're doing pretty well.